Chapter 19, the nucleus. So here we're going to be talking about nuclear stability, and we can refer to nuclear stability using thermodynamic and kinetic stability. So we define the thermodynamic stability as the potential energy of a particular nucleus that's compared with the sum of the potential energy of the neutrons and protons it's made up of. And the kinetic stability is used to describe the chance that a nucleus can undergo decomposition to form a different nucleus. And that specific process is called radioactive decay. So radioactive decay is the process of changing a nucleus into another. And then the kinetic stability gives us the probability that that might happen for a particular substance. So many nuclei are radioactive. They decompose, forming another nucleus, producing one or more particles. For example, carbon-14 decays as follows. Where the particle that's produced is an electron, and it's called a beta particle. We'll talk about that a little bit more in a second. This equation is typical of representing radioactive decay. And what has to happen in an equation is that your mass numbers and atomic numbers have to sum up. So if you look here, 14 plus 0 makes 14, and 7, and 7 minus 1 makes 6. So in a radioactive equation, the mass numbers and the atomic numbers have to sum up on both sides because it has to be equal. So of the approximately 2,000 known nuclides, only 279 are stable, which represent 2 radioactive decay. Tin has the largest number of stable isotopes. We can basically examine how the number of neutrons and protons in a nucleus are related to its stability with respect to radioactive decay. So in this picture, you can see a plot of the positions of stable nuclei as a function of number of protons and number of neutrons. The most stable nuclides are said to reside in the zone of stability. The zone of stability, look at the red dots, they indicate the nuclides that do not undergo radioactive decay. So the red does not undergo radioactive decay. Note that as the number of protons are increasing in the nuclei, the neutron to proton ratio is required for stability also increases. So this zone of stability is when the nuclei and the proton are a 1-to-1 ratio. So some important observations for radioactive decay. All nuclides with 84 or more protons are unstable with respect to radioactive decay. Light nuclides are stable when the number of protons equals the number of neutrons. That is, when the neutron to proton ratio is 1. That's when they're stable, very light nuclides. However, which means light atoms, right? So however, for heavier elements, the neutron to proton ratio required for stability has to be greater than 1 with the increasing number of protons. Certain combinations of protons and neutrons seem to confer special stability. For example, nuclides with even number of protons and neutrons are more stable than those with odd. So just a couple little observations. For our light molecules, it's important that the number of protons and neutrons are the same. For the heavier ones, the protons are going to be greater. And observations have been made that different combinations of even protons and neutrons are a little bit more stable than those with odd. All right, so here are types of radioactive decay that we'll be talking about. We have the alpha particle production, spontaneous fission, beta particle production, positron production, and gamma ray production. alpha decay, alpha particle production. So what is alpha particle production? Radioactive nuclei can undergo decomposition in various ways. These decay processes fall into two categories: those that involve a change in the mass number of the decaying nucleus and those that do not. An alpha particle is a helium nucleus. Alpha particle production is a very common mode of decay for heavy radioactive nuclides. It occurs when an unstable nucleus emits a particle composed of 2 protons and 2 neutrons, which is a helium particle. So our alpha particle is 4,2He, where again the 4, that's your mass number. The 2 is your atomic number. And then helium is your chemical symbol. So when an element emits an alpha particle, the number of protons in its nucleus changes, transforming the element into a different element. We symbolize this through another nuclear equation, which is just an equation that represents nuclear processes such as radioactivity. For example, our parent nuclide would be uranium. When uranium undergoes alpha decay, it would lose 4 total mass numbers because the 4 represents 2 protons and 2 neutrons. So 238 minus 4 is 234. And then 2 minus 90, because that's just the protons, the atomic number, 92 is 90, which is thallium. Which then, to balance out, we would write our alpha particle. So this is our alpha particle decay equation. The uranium is the parent nuclide. And then the thallium is the daughter nuclide, what was made. Now, another alpha particle producer could be thallium. So what could happen would be, if we had 230 and 90 thallium, take a moment to complete this alpha decay equation on your own. Well, if it undergoes alpha decay, that means you would have 230 minus 4, which is 226, and then 88. And you would look up any element by its atomic number. This would be radon, plus your alpha particle. It doesn't matter if you write your alpha particle first on the left side or last. Where here thallium is your parent nuclide, and helium, again, your alpha particle is your alpha particle, and radon is your daughter nuclide. So the original atom is the parent nuclide, and the product in the decay is the daughter nuclide. Unlike a chemical reaction in which the elements remain their identities, in a nuclear reaction, elements often change their identities. But like a chemical equation, a nuclear equation must be balanced. So the sum of the atomic numbers in both sides of a nuclear equation must equal. The sum of the mass on both sides also must equal. We can deduce the identity and symbol of the daughter nuclide in an alpha decay from the mass and the atomic number of the parent. So during alpha decay, you think that the mass number decreases by 4 and the atomic number decreases by 2. So you always look at how it changed by the atomic number to then figure out what the new element is, the new nucleus. So another decay process in which the mass number of the decaying nuclide changes is spontaneous fission, the splitting of heavy nuclide into 2 lighter nuclides with similar mass numbers. Although this process occurs extremely slowly, it is important in cases for molecules such as cerefia, where spontaneous fission is very predominant. So a really common process is part of this decay, spontaneous fission, where a heavy radioactive molecule is split into two lighter molecules. So instead of just a particle and then a new nuclei, a heavy nucleus is split into two nucleus. Beta production. So beta decay occurs when an unstable nucleus emits an electron. So how does a nucleus, which contains only protons and neutrons, emit an electron? Remember that the nucleus is in the middle of an atom, and it has protons in it and neutrons, which are neutral. The electrons are a cloud around nucleus. If we are just talking about nucleuses, when we're talking about radioactive decay, where does an electron come into play? Well, in some unstable nuclei, a neutron changes into a proton and then emits an electron. Beta decay is when a neutron becomes a proton and an emitted electron. We represent this by saying that you produce a beta particle. So the -1 here reflects the charge of the electron, which is equivalent to an atomic number in a nuclear equation. So when an atom emits a beta particle, its atomic number increases by 1 because it has an additional proton. For example, in the nuclear equation of 238 radon, not 238, 228. If this undergoes beta decay, the neutron makes a proton. So you increase in atomic number. Mass number is the same. And you lose an electron. This happens because the reason it goes from 88 to 89 is because a neutron changed into a proton. So you still have the same number of neutrons and protons, which is why the mass number doesn't change, but the atomic number went up because a neutron went into a proton by emitting an electron. So notice, is this nuclear equation still balanced? Yep, because 89 minus 1 would be 88. 0 and 228 is 228. So beta radiation is like a four-door car of radioactivity. Beta particles are much less massive than alpha particles and consequently have a lower ionizing power. But because of their smaller size, beta particles have a higher penetrating power, and only something as substantial as a sheet of metal or a thick piece of wood stops them. So they don't occur that often, but when they do occur, they can't really be stopped. Gamma ray. Gamma ray emission is significantly different from alpha or beta radiation. Gamma radiation is a form of electromagnetic radiation. Gamma rays are high energy, very short wavelength photons. The symbol for gamma radiation has 0 mass number, 0 atomic number with a gamma sign. So a gamma ray has no charge and no mass. When a gamma ray photon is emitted from a radioactive photon, it does not change the mass or the atomic number of the element. Gamma rays are usually emitted from the nuclei in an excited state or in conjunction with other types of radiation. What does it mean when I say excited state? So when light hits a metal, and that metal has an electron in one energy level that then jumps to another energy level, it becomes excited. Meaning, if it jumped from 1s orbital to 2s, it's still in the same atom, but it became an excited state. So when we're looking at gamma radiation, we can look at the nuclei emitted in the excited state. So, for example, alpha emission of uranium, 238, would give us and the emission of a gamma ray. So the emission of gamma rays in conjunction with other types of radiation is very common, that it's often left out of nuclear equations. So nuclear chemists simply understand that the gamma rays are emitted along with other types of decay. However, in some instances, there can be a delay between the initial decay and the subsequent emission of a gamma ray. The initial decay leaves a daughter nucleus in a metastable state, which is an unstable state that exists for a long period of time. The daughter then emits a gamma particle at a later time, for example, technetium. 99M and 43. Now notice how there's an Notice how there's an M by the mass number. That means it's metastable. That means it existed unstable for a long period of time, which then after a while gives off a gamma ray particle for gamma ray emission. Gamma rays are like motorbikes of radioactivity. They have the lowest ionizing power, but the highest penetrating power. Imagine a motorbike zipping through a traffic jam. Shielding gamma rays require several inches of lead or thick slabs of concrete. So they can't be stopped, but they're not very common. So a beta particle, also not very common, but to stop a beta particle, you only need like a thin piece of paper. It doesn't really stop it. Gamma rays, you would need like heavy concrete in order to stop gamma rays from happening, but it's not very common. It's kind of the way to think about it. Positron production. So this occurs for nuclides that are below the zone of stability. So those nuclides whose neutron and protons ratios are too small. When an unstable nucleus emits a positron is an antiparticle of the electron. It has the same mass of an electron, but the opposite charge. If a positron collides with an electron, the two particles annihilate each other, releasing energy in the form of gamma rays. In positron emission, a proton is converted into a neutron and emits a positron. So a positron looks like this. You have zero mass number, positive, because you're making emit a positron, a neutron, electron side. So when an atom emits a positron, its atomic number decreases by 1 because it has one less proton, because a proton was made into a neutron. Consider this nuclear equation to kind of see that. So when we have phosphorus, if it emitted a positron, the mass number doesn't change because you have the same number of protons and neutrons, but a proton was made into a neutron, so the atomic number goes down by 1, releasing a positron. We can determine the identity and symbol of the daughter nuclide in any positron emission in a matter of similar ways that you've done so far with alpha and beta decay as well. Lastly is electron capture. So, unlike the forms of radioactivity that we've discussed so far, electron capture involves a particle being absorbed rather than a particle being emitted. So far everything has been emitted, but electron capture is absorbed, kind of given away by the name. Electron capture occurs when a nucleus assimilates an electron from an inner orbital of its electron cloud. So remember, you have 1s, 2s, 3s, 2p, 3p, and so forth. So when an electron takes an electron from a different orbital, you have electron capture. Like positron, the net effect of an electron capture is the conversion of a proton into a neutron. We represent electron capture in the following nuclear equation. You have your proton and the electron that then have a change with a neutron. So when an atom undergoes electron capture, its atomic number decreases by 1 because it has one less proton. So for example, uranium, 92. Captures has electron capture, which then will change its atomic number by 1, but not its mass number. Now let's put all of that together. Write a balanced equation for each of the following processes. So you have carbon, which produces a positron. So again, let's first think, what was a positron? A positron was 0 plus 1 electron. So it loses a proton. So I have my carbon, which then makes a positron. So again, it tells you it's going to be decaying because it's producing a product. Have my positron, which will then give me, well, my mass number is not going to change, so it's going to be 11. And then my atomic number decreases by 1. 5. Again, 5 and plus 1 makes 6. Now you would look up the atomic number. What's the atomic number for 5? Boron. 11 and 6 on both sides, and you're balanced. Perfect. Next one. Bismuth produces a beta particle. Now, what was a beta particle? A beta particle is when you gain a proton, because a neutron is converted into a proton. So we start with the left side, bismuth. Now, I know my beta particle. I'm going to write it. I see that my mass number doesn't change, so it's going to be 214 again. And my atomic number increases by 1, so 84, because 84 minus 1 is 83. That's another way to check, which is the symbol of PO. Awesome. Again, you always look up the identity of your atom, your new nucleus, through the atomic number, not the mass number, because you have isotopes and mass numbers can be different. Last one, we have the production of an alpha particle. So an alpha particle is helium. Now it can be written like this, or actually in the form of an alpha. So we have 237, 93, and I have my alpha particle. And I know that I lose 4 mass numbers, so 233, and 2 atomic numbers, 92, which gives me PA as my symbol. And that is the different types of